Yeah.
Real glory.
Everyone has 1,000 bucks.
Yeah, I mean, a sandwich, yeah, sandwich is perfect.
If we go ahead and start. I'm very happy to have Shirley Li here today. So Shirley, her PhD under John Beacom, right, at Ohio State, and now she's a professor at UC Irvine. So Shirley, please go ahead and tell us some interesting cool physics with neutrinos.
Thank you, everyone. Thank you for the invitation. So I'll just go ahead. So the title of my talk is "What's the wave packet size of neutrinos?" So the outline of the talk is, first I'll describe what is the wave packet size of neutrinos. I'll use the symbol sigma x. And why do we want to know what it is? So the second I'll talk about, that's introduction, and then I'll talk about how currently people are estimating it. And then the bulk of the talk will be talking about how we compute this. A disclaimer, this is in prep work. It's been in prep for quite some time. So hopefully majority of the talk, I'm fairly confident that it is correct. But some of the details of the calculation we're still checking. And hopefully it will be clear throughout the talk which part we're sure of and which part we're still checking. And this is in collaboration with the lead author of the project, is a PhD student, Gustavo Alves, and also with Pedro Machado from Fermilab, and Yingtian Song. Okay, so first, to introduce what is sigma x, let me give an extremely brief reminder of how the basic neutrino oscillation framework works. And so first, this is just on standard model. So we know standard model. There's three flavor eigenstates, and three mass eigenstates. So it's a 3x3 mixing. But the purpose of my talk doesn't really matter, so let's stick to the simpler example of just two-level oscillation. And this is something that you might have seen. This is like a first-year quantum mechanics oscillation system. That if I have two flavor eigenstates, and they're connected by some sort of mixing matrix to mass eigenstates, things would oscillate. And the typical derivation lasts like 4 or 5 lines, it's super straightforward. And you can very neatly get this result that if you just have two flavors, you can derive the oscillation probability sine 2 theta squared, sine square delta m L over 4e. Okay, so hopefully this all rings bells. Now this is perfectly fine, and extending this to 3 flavors with matter effects and stuff, and we're totally able to compute this, and this has been tested in all our neutrino oscillation experiments. So we know that this works extremely well. However, if you actually look at the derivation, the typical half-page one, there's a bunch of conceptual mistakes, very obviously. And the basic assumption that is wrong is that neutrino is a plane wave. Where you assume it's in the momentum and energy eigenstate. And that is a core wrong assumption, and you can very easily see some of the conceptual mistakes. For instance, we know the oscillation has to depend on L, and this is obviously tested. However, if you really treat neutrino as a plane wave is equally state uniformly in space. So plane wave should only has a time dependent and not a position dependent, because plane waves are not traveling. So one basic consequence, if you assume it's a plane wave, is that anything you derive only depends on function of time and not location. So there you have to then argue that, we know the neutrinos are traveling at speed of light, so I'm just going to replace t as L. This is one of the steps, which seems fine, but you really think about, you can't have a plane wave that's uniform everywhere, and then say that this wave somehow is traveling at speed of light, right? It's logically inconsistent. So there's a bunch of mistakes like this, but somehow lead to the correct result. Any questions at this one? No, okay, so these conceptual mistakes, however, are well appreciated for a long time. We do have a correct conceptual picture. And that's that you treat a plane wave. Instead of treating it as plane wave, you treat it as a wave packet. Super simple, so instead of treating this as a, let's say, in momentum space, as a delta function, rather you treat it as some sort of, Gaussian dispersion. Let's say with sigma p. And this means once you Fourier transform it to position space, it's also a Gaussian shaped wave packet, and with the width being sigma x, which is inverse sigma p for a Gaussian wave packet. And, sorry, is there a question? No. Okay, and the conceptual picture is actually pretty nice. So let's say I produce at the source nu mu or nu e, one of the flavor eigenstate. And I should really think about it as a overlapping two mass eigenstates. And then plane wave packet travel in space.
So that was a picture in space or in time? I mean, in space they would be so why aren't they on top of each other?
When they're at production.
Yeah.
And as they travel in time.
Oh, that wasn't T, I thought that was T equals 0, I misunderstood. I thought for some reason rather you were saying that they were produced. So they should be on top of each other.
Correct, at production, yes, this is me trying to draw them on top of each other.
Oh, okay, sorry.
With two lines.
Okay, sorry, I thought you, excuse me, thank you.
Right. So then as time goes on, they'll do two things. One is wave packet will spread. Another thing is because they have different mass, they have different velocity, so they also have different work velocity, so they'll separate. So I say intermediate state where they got fatter and they separate a little more. And of course, if you go a very, very long time, they should be completely separated. Like this. So this is a picture. And then with this, everything is conceptually consistent. It explains why that works. However, an important prediction.
A question. So is it a wave packet in momentum space or in energy? I mean, this is a minor difference, but up to masses it may matter. Right?
Great question. So typically you expand this in momentum space, and then they would have. I write it like this.
Which means their energy distributions are slightly different, right?
Exactly.
So, okay.
Correct. So the different momentum is the thing that drives it getting fatter, but the energy difference is the thing that drives it, like relative shift. Okay. So this picture is nice, but the full oscillation probability predicted from this is not that. So there's this overall amplitude sine 2 theta squared, that's the same. But rather than the typical L over E, this looks like this. Half minus half cosine dot m squared L over 2E and an exponential term. Look like this. So you can either do trigonometry really quickly or you can take my word for it. So what this predict is...
Sorry, I apologize, I was late. What is L sub co?
This is a new scale coherent length, which has some dependence of E squared sigma x, that's the wave packet size, over Lm squared. Right. So what this means is following. If the propagation length is very short, meaning that, the wave packet, the relative wave packet, they're just starting to separate or they're barely separating, and you can sort of neglect the fact, so they're basically fully on top of each other. So then, of course, this is basically 1, this term is 1, and this reduces back to the standard scenario, which is what we have here. However, this is saying...
So basic question, are you doing this in 1 dimension currently, or are you...
yes, everything is simplified to 1 dimension.
Yeah.
However, if we set up our experiment that it goes with a very long time, like in this regime where things start to significantly separate, then basically there's some damping of the oscillation. Because you sort of have to see each other, like the wave packet, to interfere. And if their only tail is overlapping, that would affect the oscillation probability. Good. And the standard assumption is always the following. We try to do oscillation experiment over a very long baseline. But practically, terrestrially, the longest baseline we can have is size of Earth. And let's say current experiment is sort of reaching this size of Earth. But that is still expected to be much shorter than the coherent level. So meaning that whenever we set things up on Earth, we're always in this, barely separating regime. That this is not observable.
This depends on sigma x, which depends on the production. So can you talk a little bit about that?
Yes, that's the majority of the talk.
Oh.
Yes. Right, so important thing is we know what energy is, we know what delta m squared is. The key that determines coherent length is what is the initial wave packet size.
What about solar neutrinos?
Great question. So for anything coming from outside the Earth, and this is, not sure if you can, so okay, you can see. So if things are totally decohere, so if L is super big, this kills this term, right? You're just in this half sine squared. So you're in this average out regime, which might be what's happening with any astrophysical neutrinos. However, at the same time, for any astrophysical neutrinos, you're also averaging over this just from many, many different oscillation length happening. So for anything coming outside the sun, Earth, it's always in this averaged out regime where we can't tell whether it's because of many oscillation length or because things have decohered. So that's an open question. It would be great to know if we actually could possibly observe this for like ice cream or something, but it'll be a different calculation. Okay, and here, so just to add on, so the standard assumption is for any kind of terrestrial experimental setup, the production mechanism, accelerator neutrinos, reaction neutrinos, all of them. This length is always significantly larger than this, which is so we cannot observe this. And in fact, we have fit this standard oscillation formula for all our neutrino experiments, and everything seemed to be fine. So that seemed to be consistent. Okay, so that's the claim up to a few years ago.
Does this coherence length, which had this delta m squared, does that also have in medium effects too? Like,
Great question. I don't know that. We only consider vacuum, which we're barely figuring out. So.
Okay.
I think there's some argument that to first order it should not matter. But I can't say I fully understand the detail to be totally sure that's correct. Okay, so that's what. Okay, so that's the status up to a couple years ago. A couple years ago, there's a paper came out that claimed the following. So you can see that, the coherence length depends on how fast things are separating, which depends on the mass square difference, right? So you can see here it's inverse to mass, delta m squared. So the statement is sure for the standard 3-flavor neutrinos where we have mu1, mu2, mu3, and then we all know what is the size of delta m squared available. indeed, you cannot observe this. However, as you may have heard, there has been, very tentative experimental hints that point to the existence of a sterile neutrino. And this goes by like this, say the short baseline neutrino anomaly, and that say that we could possibly have a sterile neutrino that's at about 1 eV scale, which is not confirmed. However, if the argument is, if this is indeed what's happening, then you can see the delta M square involving 4 and something else would be much, much larger because it's very heavy. So if delta M square is much larger, things would go at very different speed, and separation would happen a lot faster. So their claim is that if we possibly have this 1 eV sterile, and even with terrestrial experimental setup, the baseline is already such that we would observe this extra damping due to decoherence. And in fact,
this coherence with this sterile neutrino, and what you're concerned about is decoherence within the regular neutrinos, no? It's not obvious to me that.
I would say their claim is to consider the oscillation between, let's say, nu1 and nu1 and nu4.
Right, which will make it, you'll see less new ones, let's say, but it won't affect the nu1, nu2, will it? Or except as higher.
That's their claim, correct.
It does affect nu1, nu2.
No, it does not. That's what they claim. They claim that this should leave the standard sector alone, which is
So first approximation.
correct, which is consistent with data, and that they say that you have to take into this account for the search for sterile, and they say this would alleviate some sort of experimental tension. So there has been many, many data sets looking at 1 eV, of course, and there's some data tension between the different data sets. They say that this would help. So that's the recent claim, and I should give a reference. So only 2 years ago. Specifically, they were looking at the reactor data that looked for the 1 eV.
Could you give some names, or at least one or two to remember?
Yes. I only write down the first author, Arguelles. This is Carlos Arguelles is the leading author.
Sorry, it sounds like you don't want to get into the weeds and the anomalies, but the reactor anomaly went away, or it's still there? I thought I heard it went away, but I don't know any.
Right, so I think there's two things. First is there's the whole short baseline anomaly, let's say 1 eV situation, and there's a reactor. And I think the thing on the 1 eV is extremely murky. The gist is that there's disappearance channel where, let's say, you're producing nu mu and measuring nu mu, or you're producing nu e, or by nu e I mean nu e and nu bar. You're producing nu e and measuring nu e, so that's disappearance channel. And there's also appearance channel where you start a nu mu beam and measure nu e. So if you assume it's 4 flavors with 1 mixing angle with 1 mass measurement, or 2 mixing angle with 1 mass difference, you should be able to predict relations between them. And we're not seeing that. So there's a lot of tension, there's quite significant tension between the disappearance and appearance channel in both accelerators and reactors. Now specifically you're talking about reactor anomaly that claim the disappearance, like overall shift of something less than 10% of the flux.
Yeah.
I think there have been definitely recent claims to say that had gone away. I'm not sure that has convinced the whole community, but the claim does look very strong. Okay, so the claim is that, and this paper took a phenomenological approach. They did not compute what is the coherence length or sigma x. They just say, I'm looking at the data and there's some tension. So if I were to fit, if a certain size of the wave packet would make my data fit better, and the answer is yes. The wave packet size is something that's on the order of 10 to the minus 4 nanometer. Now this number won't mean much, but they will hopefully in a second. Okay, so that's the claim. Any other questions?
You're gonna tell us how they determine this?
Yes.
Oh, okay.
Right. So in this paper, they did not determine this from like a theory consideration. This is a fitting to data. They say, assuming this is a free parameter, and I'm gonna.
What are they fitting?
Reactor data, reactor experiments.
Where does sigma x appear? Is it,
They just fit this oscillation probability,
they fit that with the exponential?
correct?
Oh, I see.
Right, and claim that this provides a better fit
I
than, it being infinity. Okay. So that's the motive, of course, this is a very strong claim because, it adds to, I guess, the possible detection of a 1 sterile neutrino, and also the claim would be that we have observed neutrino oscillation in a regime we never observed before. So that finishes the introduction. And the next part is we got interested in this problem at this point, and we're like, well, okay, so is this, data-driven fit of sigma x value reasonable? So then let's look at what have people computed before. So the main takeaway is that there's no, like, what I would call calculation. Mostly it's order of magnitude estimates. And it goes like the following. So let's think about reactor neutrino. People say, if we want to know the sort of like position or certainty or something of the neutrino, then you could argue that that should go as inverse energy of the neutrino, which is something like NED. So this is one of the claims, which will give you something like 10 to the minus 4 nanometer. It's about that size. But there are people argue differently. So, in reactor experiments, neutrinos are from nuclear beta decay. So they say the location of the neutrino it should be about the size of the nucleus. And that will give you 10 to the minus 5 nanometer. And then some people argue, okay, well, in the reactor.
I must be doing this wrong. I was doing in my head that 10 to the minus 4 nanometers was a Fermi, and that's the size of nuclei.
Right. Well, like nuclei are
Did I
not.
do the arithmetic wrong? Is 10 to the minus 4 not
It's
a
not, it's 10 minus
nanometer, not a
13.
Fermi?
10 minus
Fermi is
13,
10 to the
right?
minus
Right.
Not a
15.
Fermi.
10 to the
100
minus
Fermi.
13
It's 100
centimeters.
Fermi,
Sorry, what's 100 Fermi?
10 minus 4 nanometers.
10 to the minus 4 nanometers, 100 Fermi, you say?
Yeah.
Oh, I did the
Right.
arithmetic wrong. I probably
10 to-
added instead of subtracted something. Good.
Right, so but then some people argue others like in the nuclear reactor you don't exactly know where is the parent nucleus, right? So you cannot use this, and they argue that it really should be like you need to locate where the parent is. It really should be mean free path of the mother, which is a much larger number, something like 10 to the 2. In reactor setting. So basically the point is it's all reasonable scales, I think, to think which one it is. But of course in a nuclear reactor there are many relevant scales. And you see the problem is these differ by order of magnitude. So the data-driven number is in the range of what people have proposed. But none of this would qualify as a calculation. So it didn't go beyond this. And this is in reactor. And in accelerator setting.
Sorry, just the first argument, having it proportional to 1 over the energy, it's just because the energy is a scale in the problem? Is there
Right.
anything more? Why would it?
No, I don't really think there's more
So
reason than that.
I could have there delta M as well? It's the same, it's also,
I guess that's a little less obvious.
Well, it's not as scale.
has the same scale, so.
So I'm not sure. I'm personally, we want to compute this, so we're not advocating for these methods. But basically in the literature, people really argued about which is the right scale, and it's hard to. I felt like it's hard to say which one's correct without actually computing stuff. Let me just add this for reactor neutrino setting. This is even bigger range, something like 10 to minus 8 centimeter to 100 meter. this is basically like the length of the decay pipe, so which is like this enormous range. So this was the status before we started our paper. So to summarize, the decoherence due to the decoherence of wave packets would change the neutrino oscillation probability. So this should be a physical observable. And it was just before the recent paper, it was never thought to be possible for us to observe. And because paper came out and say that there might be some data that sort of support this, and we got interested in this quantity and want to actually compute it. So this is our calculation. And there's, because of this motivation, there's two environments that are interesting to us. One is reactor and one is accelerator. We wanted to compute reactor more, but it seems more complicated. So we start from accelerator, and that's what we look at. So the experimental setup is the following. We consider the formula beam. So you have a proton beam of something like 8 GeV, and it's hitting a block of just solid. It's about 1 meter. And then here you're producing a bunch of pions. Let's say one of these pions out here. And then in the basically vacuum decay pipe, this pion will decay to produce neutrino, and this neutrino would just go on to propagate. And this is the thing that you want to measure its oscillation of. So this is setup we consider, and we want to compute what is the wave packet size of this neutrino from this pion decay. Okay, so first we thought, so clearly the wave packet size of neutrino should somehow depend on the pion, because that's the interaction. And then this pion propagate and tracing back produced by proton. So this is to say should depend something. So this is saying the wave packet size of the pion should somehow depend on the wave packet size of the proton. And the proton accelerated from a tank, and we really don't know how to compute this. So at first we're like, this does not seem promising because it's just you push the problem back, and we don't want to know how to compute the wave packet size of the first particle. And so this was a big problem. And what we find turned out is the picture is very, very different from this. And in terms of which quantity sets the scale for the wave packet, it's a quantity that we never considered, but nor considered by anyone else. So I will outline our solution. I'll just say the punchline first. The wave packet size of neutrino is set by pion interacting with the target or environment. So this is like, Coulomb interaction or dDx energy loss sort of thing. Okay. And the main
So it's
reason.
really the uncertainty in the momentum of the pion, is that what you mean, or sort of?
No, it's
Because you don't know them.
it's literally set by, let's say, pion interacting with material.
As it gets out of the target.
Correct. Right. And why is that the important thing? The main reason is, let's just consider pion. Pion is, in this case, not a pure state. So if you haven't thought about this for a while, let's remind ourselves what's a pure state. Pure state is your particle can be described by a state like this, which is how we got a wave packet, right? If we project this onto position space, we get a wave function like this, which, for Gaussian, it's just what's the width of the Gaussian. However, for things to interact with the environment, And it's constantly, basically, every time pion interacting with the environment would take some information from the pion. So then pion become a mixed state. And the mixed state, instead of describing things as a wave function or state, you have to use the quantity density matrix. And for pure state, density matrix is simply this. But for mixed state, it is not. So to examine what the pion state looks like, rather than project it onto a single space, you have to project it onto two. So this looks like a two-dimensional function. So rather than drawing a single function like that, if it's a Gaussian, it should be like a symmetric Gaussian, like concentric circle. So I'm just going to draw it as like that. This is a pure state. So what happens when pion interacting in the environment, it will quickly become mixed. Now rather than a shape like this, it's going to go like this. So like an elliptic.
Or what are your x's?
So just like when I project the state into, for 1D, it's just for
So
pure
x
state, it's
prime
X.
is the location of the second interaction, x is where it was produced, is that more or
No,
less
so
the idea?
here I'm just describing, let's say how can I plot, like this is like a wave function for a pure state. So this is a density matrix for a mixed state. So at one time.
So it will be some decoherence time. So
Okay, so sorry, so this is generally, okay, so this has nothing to do with decoherence for now. I just want to generally introduce how we are describing our pion state. And the assumption so far has been the pion wave function is some sort of 1D function look like this with a width. But this is not correct, as in you can only use this to describe pure state. But as we saw, as we will see, the pion is not in a pure state. So at any time, instead of like a wave function, you need to draw the density matrix to describe the state.
But here, x and x prime really are coordinates,
Correct,
which you're treating as one dimensional.
correct.
But x prime isn't an interaction point.
No, so we
trying
are
to-
using this to describe pion, basically from proton production to decay, this entire time.
I'm asking if you wanted to try to calculate it from first principles, what would the calculation be?
Okay, so I will show how we evolve this in a second.
so if there is no decoherence, this is like an area preserving evolution.
Sorry, could you repeat?
This is a surface preserving evolution.
Right, I mean the evolution, so this is just how to describe the state. So we evolve it like basically Schrodinger equation. Okay, so
I'm not familiar with the experimental setup. Can you control the environment and check
So-
if this would change as you change the environment?
sort of yes, because one of the important quantity is the thickness of the target, which, you know, like at the different accelerators, this is different. So at Fermilab, you know, this has a particular density, particular thickness, and, you know, in Japan, it's gonna be different. So that's one difference. And in addition, this is the decay pipe, which is not true vacuum, right? So there's also some air density, and this is also something that can be changed. So those two things, yes. Okay, so let's see, okay, so now let's see how would while pion is interacting with the environment, like this, how would the density matrix change from a pure state to a mixed state like that? And again, the actual equation that we solved is very similar to Schrodinger equation. But you can understand this conceptually. a simple example. So mixed state from interacting with environment. So let's say initially you have a Pion state with some quantum number. And while it's not interacting with the environment, you can describe the system as Pion, environment, nothing to do with each other. And then once imagine, Pion ionized one of the electrons, so the very, very soft interaction. So in this case, let's imagine that nothing changed for the Pion because it's so soft. But what happens is that this environment, that this electron knows something about the Pion. Okay, so then the total density matrix of the system look like this. There's the Pion part, there's the environment part. And since we don't care what happens to the environment, we only care what happens to the Pion. So we care about the Pion density matrix. This should be tracing over the environment, which practically looks like the following. So this Pion part with some overlapping environment state. And since this is just an illustration example, so I don't want to write down, I can't write down the exact state of the environment, but let's imagine that the state before and after has some sort of, it's mostly the same, but a little bit different. And from this, you can see that if you're interacting many, many times, so this is from a single interaction, if you interact many times, many interaction, the Pion density matrix will look like this. The normal looking density matrix with some exponential damping. We're assuming the interaction rate is basically every time you kill off a little bit, and after many times you kill off this amount. So really what is happening here, you start from a pure state, and every time Pion interact with the environment knows a little bit about Pion position. So it's gonna kill off this like x and x prime. And as you keep going, so it's just gonna keep killing off the off-diagonal term, which is turned in from this to this shape.
Only the off-diagonal ones are decaying exponentially, right?
Correct.
Yeah.
And you can see in this example, the interaction I'm writing down is really elastic scattering. Oh, I should not erase that. So the actual density matrix evolution, just for completeness, look like this. So this is just from Schrodinger equation, so there's a free evolution piece that I'm not writing down. But the interaction part,
So this is as simple as x is where it's produced and x prime is where it decays. Is that accurate?
not quite.
We have to integrate over both for a given x prime, for a given observation of it.
No, I would say it's more like, it's kind of like, this is inside, like at a particular, like a physical space, like
That's
right
what I
now.
meant, x and x prime, x is where it was produced, a three-dimensional coordinate. And x prime is where it was decaying? No.
It's much smaller scale than that. So let's say this is where Pion's produced, and this is x. But this is very, very small, like x prime is over there, or decay point is over there. But it's more like inside this wave packet, x and x prime is like between these 2 points, how much are they coherent with each other? it's sort of what's reflected on this diagram, off diagonal.
I didn't understand that diagram, so I'm trying to work back to understand.
Maybe we could talk about this after.
If everybody else understands, it's great with me. I'll just shut up. I assume I might not be the only confused person. If it's obvious, everyone else, just say so.
No, I'm not sure.
Is
I mean,
that-
it's more that give a definition of x and x prime, just what they specifically are.
No, but it's more like instead of a wave function with the spread in x, I think, which is the probability amplitude, it becomes a probability.
X is the distance around its center of mass.
Say, so let's say just
Okay.
in 1D you have a wave packet that tells you the probability amplitude
Right.
of having that particle there, you have to square it to get it. But the environment observing it, basically, as Shirley was saying, you lose coherence between different points in space. So it becomes the value of the density matrix is the probability for the particle to be there. So you don't have coherence over large distances anymore because the environment has observed.
Yeah, no,
That
I
the
get
pattern
the
is there.
philosophy,
Yeah.
I'm just not understanding the concrete.
But the point is that so the value of x and x prime are very similar. So like, decay point and production point would be different over like hundreds of meters. But here, you're thinking about the coherence like of a state. So I would say you only consider x and x prime, within sigma x of each other or something like much smaller scale. But I'm not sure I could give a better explanation.
I was thinking microscopically, are we talking about like the typical separation between nuclei and the target, or?
Well, so
or, I mean,
the size,
right, because you're trying to figure out what the spread is, so it,
right, so I will show our numerical result, but it's something like femtometer or just 10 to the minus 10 meters smaller, a very small scale. Okay, so to evolve so basically we solve the density matrix evolution using that. The specific form we use, we consider just elastic scattering like that. Where we want the biggest cross section because we want most frequent interaction as frequent as possible because you don't need the interaction to change anything about the pion. And the winner in this case is just multiple covalent interaction. Where given the density of the material and specifics of the material, you can look up the cross section. And the value is something like it maps onto the unit in a specific way. And so the way we solve things is there's an initial, so this is a differential equation, so you need an initial state. Initial state is what do you think the pion density matrix is when it's produced by a proton? And that we don't know, because we don't know what is the proton wave packet size, and we rather not keep going back to the calculation. So what we assume is the following. So when proton produce pion, we assume that the pion is in the pure state because it's the only interaction. And it's a pure state and has some wave packet size. And then we evolve, and then it just looks like a Gaussian circle. And then we evolve it as a propagating in the target and also in the decay pipe because there's still some molecules in the air. And we see how it turns from a circle goes to, on the off diagonal piece, it just shrinks. And this is the size that I'll label quantum. This is the size that actually matters. So let's see how they will evolve. Of the pion. As a function of distance traveling in the target. Again, the target is about 1 meter in total. And, okay, so the first thing is we don't know what's the initial value, so we scan through a bunch of initial values. So we went as far as 1 centimeter. But whatever you go, it's gonna go flat a little bit, and then like this. Or if you start from some smaller value, it's gonna converge to the overall thing pretty fast. Or if you start from really small value, it's gonna go like this.
Did you put numbers on there?
Yeah. So on the y value, we scan through something as small as 10 to minus 15 centimeter. On top, we scan through something like about 1 centimeter. And here the point is we really don't know what's the initial value. We try not to argue, so we just scan through as large a range as we think it possibly could be. And this is a log scale. So this happens extremely fast. So up to here, it's something like 1 millimeter. And the reason it happens very fast because you see it's exponential damping. So this suppression of the off diagonal happens extremely fast. And we know that, because I know this thing traveled for 60, 70 centimeter for the formula target. And you can find where this is on this curve. And this is something like 10 to the minus 13 centimeter. Yeah.
So the first expression you wrote for the Pion density matrix, you had a time dependence on the exponential damping, and now it looks like you exchanged it for a spatial dependence. Like, where do the assumptions about like the momenta of the Pion, stuff like that, come into all these numbers?
Right, so let's say, so this is time dependent because it's shorter equation. We assume the Pion travel set. We use relativity expansion, so this determines the speed.
Yeah.
Okay. So since I'm running close to the end, let me just summarize the next couple steps. I won't have time to go into the detail. So basically, we realized the important thing is that Pion is not in a pure state. So there's sort of like 2 length scales in the problem. And the important one is to understand neutrino oscillation. Obviously, you want the wave packet to be coherent with each other. So the important thing is the quantum length of the problem, which luckily we saw that it does not depend on initial condition because we cannot compute that. And this rate is, you see, it's very fast. This is entirely dependent on the multiple Coulomb interaction. It's the largest cross-section with the softest interaction in the environment. And once we figure out the Pion density matrix, the property basically entirely gets passed down to neutrinos. And you can sort of imagine this. So this is the Pion density matrix. This is now a Pion decay. At first we got tripped up in terms of how to compute something decay with not a pure state. But we realized that you can simply treat this as a collection of pure state. So you can replace the overall ellipse with just many circles. Again, circles on this plot means it's pure state. So one pure state basically maps onto the neutrino by about the same order of magnitude. I skipped a bunch of math, but the point is that one circle corresponds to 1, exactly like follows. And finish this one. So in this process, roughly speaking, the wave packet size of neutrino is, let's say, within a factor of 1 to 2 from the wave packet size of the Pion. So at the order of magnitude level, that's something like 10 to minus 13 centimeter. This is the same. Okay, so this gives us the calculation for wave packet size. And this factor is the part we're still not sure of. And since I won't be talking about this, I'll just skip that, but happy to check after. And when we first started doing this calculation, we thought, we do not think this should be observable, it's just gut feeling. So we thought whatever we compute, we can prove that this is not experimentally observable, which is also why the first round we were quite sloppy with factor of 2, because we didn't think it matters. But with this number that we had computed, we were looking at what's the coherence length we would get for accelerator neutrinos as a function of delta m squared, because we have the sigma x. And what we see first, lying like this log scale, that at 1 eV square, which is this possibly sterile neutrino oscillation, the coherence is something about 1 kilometer, which was alarming to us because we obviously have experiment at 1 kilometer separation. So we're like, wait, this is possibly observable. But then it's the 1 eV, but if you, which might not exist. But if your delta m squared is 10 to minus 3, which is the standard mass splitting difference between U2 and U3, this is something like 1,000 kilometers. Which is where long baseline experiment sits. And this is where short baseline experiment sits. So according to our current number, it seems to be this potential decoherence effect, again, which comes up in the damping of the oscillation probability. Our calculation is claiming that this might be an observable effect in future experiments, which was not the conclusion that we thought we would get, which is why now we're double checking all factors 2. So I'm not certain about factors 2. And you're in exponential, factor of 2 really matters. Okay, so that's our conclusion. Summarize. So the wave packet decoherence is, everyone agrees that it could lead to a change in oscillation probability, which should be observable. So other argument in literature is about what's its size. And before, it was never actually computed, it was always estimated. So we set out to figure out how to compute it, and our formalism looks quite different from what we were expecting. And the key thing that for us to find is the whole thing is set by Pion environmental decoherence. So it's a scale that was never considered before. And number-wise, it's something like 10 to minus 13 centimeter, which might be observable. That part remains to be, clearly checked. So that's the summary. Thank you.
Question for Shirley.
I mean, the whole calculation, which gives 10 to the minus 13th, is based on, as you say, the environment of the pion.
Yeah.
Is it possible to change experimentally the environment of the pion in a way that could start to matter and that you might actually be able to test experimentally?
Sorry, so the only test we can think of is neutrino oscillation, but what are you talking about
Maybe
measuring?
it's like making a denser target.
For
that
instance.
sort of thing.
So one thing that we can easily compute is the beam in Japan. So I don't know their specs yet, but this is computed for Formulab, so this is for
Right.
doing setup. So I guess we could be in a situation where this is observable in the US side, but not observable in Japan because the target size is different.
Right,
That's a good point. I don't know the specs.
okay.
Do you consider the interactions within the parent nucleus where it was produced, because they must use heavy targets? And I could imagine, right, the cross-section is what it is, but the density is incredibly big. And so multiple interactions in the target might do it for you. And then it would become quite a different number, I think.
So,
well,
sorry, could
of
you
order
be,
of the size of it.
could be more specific about which interaction you're thinking about?
When the first interaction happens, the PP interaction you're talking about where it's produced.
Yeah.
You've got this charged pion and now it has to plow its way through a lead nucleus.
Yeah.
At extremely short distances so that the scattering is extremely strong.
Right, that's a really good point. So I did not explain that. So so in terms of decoherence, basically our understanding is that it doesn't matter how hard the interaction is. So normally we care about hard interactions, ignore the soft ones.
No, I understand there's soft interactions. I'm just saying that because the density is so high locally,
Mhm.
it could have a big effect even though it's a short physical distance.
I see.
The distance is very high and the sort of impact parameter is extremely small compared to an average interaction. So if you
Right.
haven't included it, you might want to look at that.
Yeah, that's a good point.
I was gonna ask, like, so you've got it down to a factor of 2 uncertainty, like what do you think is the leading order of contribution to the uncertainty now then?
Good point. So we're sorting out a bunch of factor of 2, so total may be larger. But some of so for us, the confusion is more conceptual than numerical. So for instance, here, the picture is kind of simple, but let's say how to treat decay. So what we know is that for decay, we work in momentum space, but then you can just Fourier transform everything's Gaussian. So let's say you start from a Pion density matrix in P and P prime, and we know that this maps exactly into neutrino plus muon system. Like this. This mapping we figure out is exact. However, then there's the muon hanging around that you're not measuring. So we only care about what happened to neutrino, so you need to trace over the muon. And we run into some combination of conceptual and numerical problem where we trace over the muon. And that introduced one factor too. For instance, you can't trace it assuming muon's a plane wave. So that you sort of have to assume muon also has a wave packet size, which is an additional scale we didn't want to introduce. But we can't totally get rid of it other than saying it's between like 1.5, the final effect. So that's at least a factor of 2 there.
For like normal neutrino oscillations, I thought there's some cases where you can have like, the strong interactions or damping can actually like prevent decoherence in some sense. Like if you have some, like imagine you create some like given flavor state and normally like you will oscillate or it will change into some other flavor state. If the scattering is slow compared to this oscillation rate, then you have, on average every time you make a scattering or a measurement, you're producing a little bit or you're measuring some sine squared 2 theta probability of being in this other state, and as you said, you exponentially build that up. But if your scattering is so fast compared to like your oscillation rate, then you don't have time to actually oscillate and produce this other state. And so you're stuck in this quantum Zeno-like effect. Is there something similar like that in this? I mean, is there another time scale that you have to compare with? Or, I mean, is analogy even fair or is it similar?
So I think what you're describing, I can see it, one should carefully examine this in something like a supernova where the interaction rate is so high. But generally here, the neutrino interaction rate is quite low, right? Because neutrino, so this is pion going through medium, but neutrino interaction part is, most of them don't interact. Occasionally they either one interact in the near detector or the far detector.
Right.
So this is, for neutrino, this is not in the
Right.
dense environment situation.
Right. I mean, is there something analogous for the pion though?
Not in our framework, because again, Pion doesn't have, so for us, I think Pion doesn't have additional flavors.
Yeah.
So the only quantum information it carries is just, really position that we consider.
Right, but it's a mixed state. Like when you're using a density matrix to describe the mixed state, it's a mixed state of different. Yeah, so it's a mix in what sense?
I guess it's that the target also has something on the Pion location.
Location wise, okay.
Because every time you ionize, the electron sort of knows where the Pion is.
Okay, position wise, okay.
Right.
Sorry, maybe I missed it, but before you mentioned the paper that first proposed this relevance for EV steriles and they fit this parameter.
Right.
How did that compare to the scale that they found?
Okay, so numerically, I think they're within something like an order of magnitude. However, that is fitting for reactor neutrino only, and our framework works for is specific to like Fermilab accelerator. So we would have to do a whole different calculation for
I see,
reactor.
it's not directly relevant, sorry.
Right. So we wanted to, once we figured this out, we wanted to figure out how to compute reactor, but that seems, harder.
Sorry, I was a little confused by, did you say the 10 to the minus 13, like depending on the density of the target, that can vary? Or,
Correct.
like to what, like what's the ratio of the variance? Like say I double the density of the target, what happens to the 10 to the negative 13?
Roughly twice.
Oh, okay.
Because so this line is something like square root of lambda t. So square root of, 1 over square root of lambda. Okay, so maybe like a 1.4. So this line goes like 1 over square root of lambda, like this. And lambda is interaction rate, which I think for like this kind of interaction, it just scales with density linearly.
Okay, gotcha. Thank you.
Any last questions for Shirley?